Hello, Professor. My name is Muhammad Tariq, and my student ID is F7290. And today I will explain the article titled Fully Distributed Algorithms for Constrained Non-Smooth Optimization Problems of General Linear Multi-Agent Systems and Their Applications. So this paper published in IEEE Transactions on automatic control, and it addresses a critical challenge in distributed optimization, that how to solve a complex, non-smooth problems that involve multiple agents working together under constraints. So I will break down its concepts step by step so that it will be clear to understand. So next slide. Yeah, introduction. So first, let's understand why distributed optimization problems or how it matters. So these problems involve several independent entities or agents like robots or power systems that needs to make decisions collectively. Examples including managing power generation in smart grids to minimize cost or coordinating autonomous vehicles to achieve a common goal, actually. So the challenge here is that each agent operates under its own constraints and rules, and the overall optimization is complicated further by factors like non-smooth cost functions or communication limits. So this, sorry. So next slide is problem statement. Why it is not working? Yeah, sorry for that. So let's start with problem statement. So actually, this paper focuses on solving a specific optimization problem. Imagine a network of agents, each with its own goal, but collectively, they aim to minimize a total cost function. So the optimization also needs to respect two types of constraints. There are local constraints which apply to individual agents, and second is coupled agents. Coupled constraints. Yeah, so which involves the interaction between all agents. So this is the equation, which the optimization problem can be expressed by this mathematical equation, where Fi yi is the non-smooth cost function, which is specific to each agent, and this part, Wiyi, which is less than equal to Wi, is which donates the local constraints for each agent, and the third one, Diyi is the representation of the couple constraints that involve interaction across agents. So let's move to the next slide, key challenges. So this problem is difficult for three key reasons. There are, uh, sorry, yeah, three key reasons, which are agent dynamics, which the behavior of agents is governed by complex linear systems. It means that they cannot make decisions directly. So second is non-smooth functions. The cost function are not smooth, making standard optimization methods ineffective, actually. So the third is coordination, which is the agent must coordinate with limited information, actually, because with respecting both their own constraints and also the global ones. Yeah. Yes. So this is the proposed solution. So the paper proposes two algorithms to solve these problems that I mentioned. The state-based algorithm, which assumes the agents have access to their full internal state, and the second is the output-based algorithm, which only relies on the observable outputs of the agent, which makes it more practical for a real-world application, I would say. So in the next slides, I will mention their real-life examples also. So let's go for that as well. So how the state-based algorithm works. So let's start with it. Each agent has its own dynamics actually, represented by the equation xi is equal to ai xi plus bi ui. So xi represents the internal state of the agent, such as its position or velocity, and same as for the UI is a control input that guides the agent actually. So the goal is to design UI. So the agent stabilizes and solves the optimization problem. The control input is calculated using the equation which is in the next slide. This is the equation. So I would give the real world example also, which is related to smart grid economic dispatch. So imagine a smart grid where each power plant, like agent, must decide how much electricity to produce uh, to to minimize the total cost of generation while meeting demand and respecting each plant's capacity actually. So in state-based algorithms, if we use it, so what will be the steps to solve it? I will gonna tell you that first would be the collect state data. So in each plant monitor, its power output and system state like fuel usage or temperature. So second would be the share information with neighbors. Each plant communicates with nearby plants about their output and cost trends. And third would be to adjust based on constraints. It if I mean if many plant exceeds its capacity or if overall demand isn't met, so adjustments are made. So last would be the iterative process. The algorithm updates each plant's controlling to gradually move towards the optimal solution. So the analogy of it is to consider a group of farmers trying to collectively decide how much water to use for irrigation. So each farmer shares their water usage and they needs with they need with neighboring farms. If one farmer is using too much or too little water, they obviously adjust based on shared information. So it aiming to the minimize total water, so it use while ensuring all crops get enough water. So this was the example of it. Let's move to the next algorithm, which is output based algorithm. So in this algorithm, it is used when the agent's internal state is not directly observable. In this case, the algorithm estimates the state using an observation equation, which is mentioned as xi is equal to ai xi plus bi ui plus hi bracket yi minus ci xi cap. So where x cap I is the estimated state of the agent and hi is the gain matrix, which actually the estimate by comparing predicted and observed outputs. And once the estimated state is obtained, so the control input is computed using the same approach as in the state-based algorithm, but it based on the estimated state, which is x cap I. So let me give you the example, real life example of it also, which is the I suppose a group of I mean street vendors estimates their sales, I mean their outputs. Sales would be their output based on the number of customers seen. So they adjust prices or stock based on what their neighbors report about their sales. So aiming to collectively maximize profit while ensuring enough supply for everyone. So output-based algorithm work on it. So it actually the working of it is like this. So let's move to the next mathematical foundations where we used, I mean, the author used four points for mathematical foundations like subgradient descent, projection operations, then Lyapunov stability analysis, and the fourth one is set valued Nizhel principle. So let's start with the subgradient descent. So, sorry. So in this, actually, in subgradient descent, obviously generalization of gradient descent for smooth convex function is right here, xi plus 1, which is equal to xi minus a x gx. So in this point, so I would like to share the working of it, that how it works in the uh, how the author used this point to its problem. So the working of this thing is this subgradient descent is it used to handle non-smooth cost functions actually. So unlike gradient descent, which I mean requires smooth functions, so it works with functions that may have sharp corners. Let me give you the example of it. Like imagine a delivery company optimizing its route costs in a city with unpredictable road closures. So the cost function representing the travel time, where it would have sharp changes based on these closures. And subgradient descent allows the company to evidently it iteratively adjust and find an optimal route despite these irregulations. So it used on that thing. So second is project operations, so which ensures the variables which I may remain in the constraints. Here's the formula equation, and it projects point x onto the feasible set S. So the working of it is the role of projection operations is to ensure that the solution remains within the certain constraints, which surely for like when solving an optimization problem, it actually constraints like budget or like the time limits need to be respected. So here the example of it is was. So let's start with the next one. So third is Lyapunov stability analysis, which guarantees system stability, which this method ensures that an algorithm will not diverge and will instead converge to an optimal solution over time, I would say, to maintaining system stability. Yeah. So for the set value analysis principle, it actually the principle extends the above one, the Lyapunov stability analysis, that to non-smooth and complex systems, and it ensures that despite complexity, the system behaves remain the system's behavior remains stable and converges to a solution. So it helped on that problem. So let's start with the I mean the result of the article. So the results was that the key findings would be the paper. I mean the paper findings were include both the algorithms solve the optimization problems successfully, and both the algorithms like state-based algorithm and output-based algorithms showed the slightly better stability, conversion speed, and I mean, fully distributed and no central control is required for the initialization free. They don't require specific starting conditions. So it would, the result was I mean, it required, it actually gave the best output that the author was finding, was expecting actually. So for the next slide, it is my recommendation and the criticism from my side. So I would recommend improving the algorithms. I mean to make them adaptable to real time, more dynamic conditions. Currently, they actually work under fixed constraints. So like, but real world systems often face changing scenarios such as fluctuating electricity demand or varying generator outputs. So, enabling the algorithms to adjust in real time would enhance their effectiveness and application in real world algorithms, I would say. And the another important recommendation is to explore whether these algorithms can be extended to nonlinear systems, and the the current design focuses on complex problems, obviously, but the non-linear dynamics. But in the real world scenarios, such as complex energy distribution systems, often involve the non-linear dynamics. I think so. Adapting these algorithms to handle such systems could significantly broaden their application and across different types of optimization problems, it would help there. And secondly, the criticism from my side would be the algorithms have certain limitations, obviously, no doubt about that. So one major issue is their reliance on the assumption that the problem is convex. Yeah. So this assumption may not hold true for all systems, particularly in non-convex situations. As a result, the algorithms might not perform as well when applied to problems outside the scope. So another challenge is computational expense. So when dealing with the large-scale systems involving many agents, the algorithm can become quite costly, actually, in terms of computation. And the interaction between multiple agents require significant processing power, which make it difficult. So they scale the algorithms efficiently for large system or for real-time application, I would say. So that was my criticism. So my personal view is I may expand it like this, like the problem is clearly explained as I address the shortcomings, and the method is distributed optimization, and the use of the smart grid shows how this research is useful in the real world situations, and to expand the research to include non-convex problems, which I mentioned in my recommendation also, that would make the results more applicable to a wider range of challenges. So, in conclusion, the paper actually tackles a complex optimization problem, which involve the non-smooth functions and constrained system. It introduces two innovative algorithms that are practical and effective for real-world application like smart grids. So these methods are fully distributed, robust, and initialization free, and making them highly impactful for cyber physical systems. So yeah, that was it. And the future work would be the address scalability and non-convexity challenges and expand to other real-world applications like robotics and autonomous vehicles. So that would be great for future. So yeah, this was my article number one. And yeah, lastly, I have two questions, two final examination questions, which I mentioned here. And lastly, yeah, so that was it. So thank you so much for your attention.